Hello everyone. So today we'll be addressing, discussing some problems on mathematical induction from NCRT, and I will just try to refer Nicholas Bona, the book name being a walk through combinatorics by Nicholas Bona. It's a it's a really good book for discrete maths and all those who are inclined towards combinatorics or number theory. It's a mixed bag of those kind of subjects. Essentially, it's a subject. It just encompasses the subject discrete maths. So, we'll be starting with the more trivial problems. You all know what the summation of first natural number, first summation of first odd natural number, summation of first and even natural numbers or square of natural numbers. You know how to prove those by induction by now, at least. So, presuming that you guys have a solid foundation regarding these kind of problems, I will just proceed with the more non-intuitive or more non-trivial, to be precise, non-trivial problems in mathematical induction. Um, okay, let's start with this problem. Prove that 2 to the power n is greater than n for all positive integers n. So you know the drill use, while using the principle of mathematical induction, right, to prove statements. Since see that we are required to prove that you just infer that this is a problem which relies on natural numbers, positive integers, and so your intuition might say that this will invoke the principle of mathematical induction somehow. I mean, that's true. I mean, you don't know the concrete reason why mathematical induction has been. I mean, why mathematical induction would be used in this scenario, because this is essentially a statement that is a statement regarding, I mean, associated with the natural numbers. So, that is why that's the exact reason why it invokes the principle of mathematical induction. So we are compelled to use mathematical induction to derive this result. In other words, so yes, so P of n is what I was referring to as a statement regarding a natural number n, which is the hypothesis that a hypothesis means we have just conjectured, or I mean, conjecture is something that we have not proven, but we just boldly state, a uh, assertion that seems to be true for a substantial amount of natural numbers, and uh, we just hypothesize that, and then just use the principle of mathematical induction to prove if the hypothesis is true or not. So that is exactly the agenda of principle of mathematical induction. So you just do the base case, that is n is equal to 1. So here for n is equal to 1, 2 to the power n is 2 to the power 1, which is 2, and n is 1. So this is obvious, 2 is greater than 1. I mean, off. I mean, I'm just everything that is obvious is not obvious. This is a this is a higher order mathematics. I mean, this requires a rigorous amount of work to derive that 2 is greater than 1, which I will not dive into. So a priori, we just have the result that 2 is greater than 1. So hence the statement P of n holds for n is equal to 1. So that is nothing but P of 1 is true. You could conclude that P of 1 is true. So moving on, you just assume that this is the inductive step, that you just assume that it holds for any positive integer k. You have to show that it holds for k plus 1. That means P of n, I mean P of k plus 1 is true whenever P of k is true. So yeah, you just proceed by like this. You just multiply 2 on both sides, and you just see that 2 to the power k plus 1 is greater than 2k. It's derived it. Since you already have this result, this is the inductive, I mean induction hypothesis. So we use this result over here and just multiply 2 on both sides of the inequality, and we got that 2 to the power k plus 1 is greater than 2k. Since k is a strictly positive integer, so k plus k is indeed greater than k. Or essentially k is greater than 0, that's why 2k is greater than k. Or to even make it even strict, or even a better result is uh, k is strictly greater than 1, because we have assumed that, I mean here we have assumed that k has to be greater than 1, because we already dealt with the situation uh, when k, I mean n was 1, so k is not equal to 1, and k is essentially greater than 1 by the trichotomy of natural numbers, which is a property of natural numbers that we learn in higher mathematics. I mean, k could, there are essentially two cases. K could have been equal to 1, or k could have been greater than 1, and nothing else. So, since k is a positive integer, which has been assumed, so since we cross out the possibility that k is equal to 1, so we're just left with this choice that k is greater than 1, and k must be greater than 1. So, here you can see that k plus k is greater than k plus 1, since k is greater than 1. Or since k is greater than 1, adding k on both sides, we get that k plus k is greater than k plus 1, which is 2k is greater than k plus 1, and 2k is less than 2 to the power k plus 1. So the overall conclusion that you could get right now is 2 to the power k plus 1 is greater than 2 k plus 1, which is nothing but p of k plus 1, right? So this holds true when n is equal to k plus 1. So here you could basically close the inductions, the induction. So, and you could conclude that p of n is true for every natural number, every positive integer. So this was a really good problem regarding induction, and I guess this is a telescope. Moving on to the next problem, I guess this is a telescopic summation problem, and it involves a slight bit of trick that I could you could adopt easily. I mean, if you go through this, so these are all trivial problems of induction. I mean, uh, this is okay. Okay, so I will just do a slight digression over here. The induction that we learned over here, that is these statements regarding induction, is this is essentially the weaker weaker form of the principle of mathematical induction. Why is it referred to as weaker? Because this is this I mean this algorithm cannot be adopted in every kind of scenario that would require induction to prove those kind of statements. There's a stronger form of induction that would be applicable in certain scenarios where this weaker form of principle of mathematical induction would not be applicable. So uh, we will not try to since the stronger form of mathematical induction is not covered in this NCRT syllabus. Uh, we can't give a motivation towards, or we cannot give a brief idea about that subject basically. So I'll just stop it right over here. So I hope you enjoyed the lecture. Thank you, guys.